Welcome back to Fun Facts Online. Today, we are going to bypass the usual pleasantries and dive straight into a topic that sounds like it was ripped from the pages of a cyberpunk novel, but is actually happening right now in nanophotonics labs from Michigan to Hefei. We are talking about the end of darkness. We are talking about upgrading the biological hardware of the human eye. Specifically, we are going to explore the emerging technology of infrared nanovision. To understand why this is such a monumental shift, we first have to appreciate the limitations of the equipment you were born with. The human eye is often cited as a marvel of biological engineering, and it is, but it is also surprisingly limited. If you look at the entire electromagnetic spectrum, the band of reality we call visible light is just a tiny sliver. Beyond the red edge of the rainbow lies a vast ocean of information called infrared radiation. It is surrounding you right now. It is the thermal signature of a warm body in a cold forest, the beam of your TV remote, and the energy radiating from a cooling car engine. For all of human history, we have been blind to this. Evolution gave snakes, like pit vipers, the biological sensors to detect this radiation and hunt in the dark. But humans were left in the dark. For the last few decades, if we wanted to bridge this gap, we had to rely on heavy, battery-draining equipment. We are talking about bulky night vision goggles that use thermal imaging, which often requires cryogenic cooling to reduce noise, or image intensification, which amplifies starlight but fails in total darkness. But the era of clunky green goggles is ending. A quiet revolution is taking place that marries the atomic scale precision of graphene with the unique quantum properties of upconversion nanoparticles. The goal is simple but radical: to shrink night vision capability down to a transparent layer lighter than a feather and thinner than a strand of DNA, sitting comfortably on the surface of your eyeball. There are currently two main technological philosophies driving this research, and we need to break them down because they approach the problem from completely different angles. The first path is the electrical interface, pioneered largely by researchers at the University of Michigan. They turn to graphene, the wonder material consisting of a single layer of carbon atoms. Now, graphene is incredibly strong and conductive, which makes it great for electronics, but it has a flaw when it comes to vision. It is almost entirely transparent, absorbing only about 2.3% of light. If you want to build a sensor, you need it to catch light, not let it pass through. To overcome this, these engineers created what we can call a graphene sandwich. They placed an insulating barrier between two sheets of graphene. The mechanism here is fascinating. When light hits the top layer, it frees up electrons, creating positively charged holes. These quantum effects are then amplified by the bottom layer of the sandwich. This turns a very weak optical signal from infrared light into a strong electrical one. The result is a sensor smaller than a pinky nail that can detect the full infrared spectrum without needing those bulky cooling systems used in traditional thermal cameras. The ultimate goal for this graphene approach is to integrate it into a smart lens that acts as a transparent heads-up display, or HUD, feeding data to an external device. However, there is a second approach that is perhaps even more sci-fi because it skips the electronics entirely. This approach, pioneered by researchers at the University of Science and Technology of China and UMass Chan Medical School, relies on physics rather than circuits. It creates a direct retinal projection using something called upconversion nanoparticles. This is the part that really bends the mind. Usually, in physics, we deal with down conversion. Light travels or bounces, and it loses energy. But these nanoparticles are engineered to do the exact opposite. Imagine these particles as tiny light antennas. They are designed to absorb multiple low-energy infrared photons, which we cannot see, and combine their energy to spit out a single high-energy visible photon, which we can see. Let's walk through exactly how this works in a contact lens. The lens is embedded with nanoparticles made of a crystal called sodium gadolinium fluoride. These crystals are doped with specific elements like erbium and ytterbium. When near infrared light, specifically wavelengths between 800 and 1600 nanometers, hits the lens, these particles catch that energy. They then instantly re-emit that energy as green, red, or blue visible light. So if you are wearing this lens and you look at an infrared source, your eye perceives it as a glowing green image. Because the lens is transparent, you can still see normal visible light at the same time. It is effectively an augmented reality overlay powered by the laws of physics, not by a battery. Now you might be wondering, how do you actually put this on an eyeball without damaging it? Creating the material is one thing, but biocompatibility is a massive engineering challenge. You cannot simply dust nanoparticles into an eye. To ensure safety, engineers utilize a sandwiching technique similar to the graphene approach, but using polymers. They encapsulate these crystals within a highly breathable, FDA-approved polymer. These are the same hydrogels used in standard corrective contact lenses. This ensures that the active sensing layer never directly touches the cornea, preventing irritation or toxicity. Another major hurdle was the blur problem. If you place a screen directly on your cornea, you cannot focus on it. It is too close. However, because these upconversion lenses are not screens but rather light converters, the light they emit passes through the eye's natural lens and focuses onto the retina, just like normal light from the outside world. Early prototypes gave a slightly watery or blurry view of infrared sources, but refinement in particle density is rapidly sharpening the resolution. So, what is the point of all this? While the phrase night vision immediately conjures images of special forces and military operations, the utility of infrared contact lenses extends far deeper into civilian and medical life. Let's look at medical diagnostics. Veins and blood vessels are highly visible under infrared light. A doctor wearing these lenses could look at a patient's arm and see the vasculature glowing beneath the skin. This would make blood draws and IV insertions significantly safer and faster. Furthermore, certain tumors and inflamed tissues have different heat signatures. A surgeon could potentially identify the margins of a tumor in real time without ever looking away at a monitor. Then there is search and rescue. In a fire, smoke, fog, and dust scatter visible light, essentially blinding rescue workers. Infrared light, however, has longer wavelengths that penetrate these obscurants much better. A firefighter wearing IR lenses could walk into a smoke-filled room and see the glowing thermal signature of an unconscious person on the floor, all while keeping their hands free and unencumbered by heavy gear. We also have applications in security and encryption. We could enter an era of invisible signage. Security codes, authentication patterns, or silent alarms could be projected in infrared on walls or screens. To the naked eye, the wall looks blank. To the lens wearer, the message is clear. This has massive implications for anti-counterfeiting measures on currency and high-value goods. There is even potential for treating color blindness. The same technology used to shift infrared light to green can be tweaked to shift other wavelengths. Researchers are exploring how upconversion particles could help the colorblind by shifting shades that are invisible to them into parts of the spectrum they can perceive, effectively restoring a form of full color vision. But perhaps the most interesting part of this research is the user experience. What is it actually like to wear them? Test subjects in early trials described a surreal experience. In a lit room, their vision is normal. But switch off the lights, and the darkness isn't absolute. Infrared sources, like the pilot light on a stove, the IR sensor on a TV, or even a specialized IR flashlight, appear as luminous green or blue beacons. Perhaps the most uncanny aspect discovered during testing is the ability to see through eyelids. Infrared light passes through human skin and tissue much better than visible light. In tests, subjects with their eyes closed could still detect bright infrared flashes, sensing the direction of the light source even while technically blind. Of course, we need to address the reality of where this technology stands today. We're not quite ready to buy these at the pharmacy. There are significant challenges ahead. The first is sensitivity. Current nanoparticle lenses need moderately bright infrared light to work. They are not yet sensitive enough to passively detect the low-level thermal body heat of a person standing in a pitch-black field, which is true thermal vision. Boosting the quantum efficiency of the particles is the primary engineering focus right now. For the graphene-based electrical versions, finding a way to power the lens wirelessly without heating up the eye is a critical hurdle. And then there is the societal angle. If anyone can wear undetectable night vision cameras or sensors, privacy in low-light public spaces becomes a complex issue. Despite these hurdles, the trajectory is clear. We are witnessing the end of a human biological limitation. Infrared nanovision is more than just a gadget. It is the first step toward transhumanist ocular enhancement. By engineering night sight into the humble contact lens, we are not just looking at the dark. We are looking through it. As costs fall and sensitivity rises, the phrase "afraid of the dark" may soon become a relic of the past, forgotten by a generation that can see the world in all its invisible glory. That is the reality of the invisible world becoming visible. Thanks for listening to this deep dive on Fun Facts Online.